In the German town of Kalkar, near the Dutch border, children spin through the air on a ride called the nuclear tornado. Behind them rises a huge concrete cooling tower. Inside it, bright chairs swing from long steel arms. Families eat ice cream where engineers once planned to make nuclear fuel. This place was never meant to be an amusement park. Germany spent about 4 billion Deutschmarks building a fast breeder reactor here. The SNR 300 was finished in 1985, yet it never entered commercial service. By 1991, the project was dead. The reactor was later sold, stripped of its nuclear parts, and turned into Wunderland Kalkar. That cooling tower is now a monument to one of the most costly dreams in energy history. The United States tried the same kind of reactor. It stopped. France built one twice as large as many normal nuclear plants. It shut down. Japan spent about $8.5 billion on its own attempt. It made almost no electricity. For decades, the message seemed clear. Fast breeder reactors worked on paper, but they were too hard, too costly, and too risky to run. Then, on July 4, 2024, a new reactor reached criticality beside the Bay of Bengal. It stood at Kalpakkam in Tamil Nadu. It was built by Pavani, a company owned by the Indian government. Its planned output was 500 megawatts, and it used the same reactor type that had left Germany with a theme park, Japan with a national scandal, and France with a vast plant waiting to be taken apart. India had entered a field that most rich nations had left behind. But why? Why keep working on a machine that took 20 years to build, missed deadline after deadline, and cost almost twice its first budget? Why use a coolant that can burn when it meets air and react hard when it touches water? The answer begins inside ordinary uranium. A normal nuclear reactor uses uranium-235 as fuel. But uranium-235 makes up less than 1% of natural uranium. Most of the rest is uranium-238, which normal reactors can't use in the same direct way. Think of a normal reactor as a baker who buys 100 bags of grain, uses less than 1 bag, and stores the other 99. A fast breeder reactor changes that math. It starts with fuel made from plutonium and uranium oxides. Fast-moving neutrons split atoms in the core and release heat. That heat makes steam, the steam turns a turbine, and the turbine makes electricity. Around the core sits a blanket made with uranium-238. Neutrons from the chain reaction strike this blanket and change some of that uranium into plutonium. The reactor can then produce fresh fuel while it runs. That is where the word breeder comes from. It can make more fissile material than it burns. Physics still sets firm limits, so this isn't a machine that creates energy from nothing. But it can draw far more energy from the same supply of uranium than a normal reactor can. There is a catch. Normal reactors often use water to carry heat away from the core. Fast reactors need neutrons to keep moving at high speed, and water slows them down. So the PFBR uses liquid sodium instead. Sodium carries heat well. It can work at high temperatures without the extreme pressure needed in a water-cooled reactor. But expose it to air, and it can catch fire. Bring it into contact with water, and the reaction can turn violent. That one choice explains why so many nations walked away. It also explains why India spent nearly 4 decades learning how to control it before starting the PFBR. The sodium problem showed up clearly in Japan. Monju was Japan's flagship fast breeder. It sat in Fukui Prefecture, on the Sea of Japan coast, and was meant to show that Japan could close its nuclear fuel cycle. On December 8, 1995, a pipe fitting failed. About 700 kilograms of liquid sodium poured into the secondary loop room. Sodium doesn't burn blue and quiet. It burns white and angry, releasing a thick cloud of caustic smoke. Engineers contained the leak. Nobody died. The physical damage was manageable. What wasn't manageable was what came next. The Power Reactor and Nuclear Fuel Development Corporation, the agency that ran Monju, filmed the damage, then edited the footage to hide how bad the spill looked. Engineers altered inspection records. Officials held press conferences with incomplete information. When the cover-up was exposed, public trust in the program collapsed. Monju sat idle for most of the next decade. A brief restart in 2010 led almost immediately to another accident. A fuel handling device fell into the reactor vessel and couldn't be retrieved for over a year. In 2016, Japan's government did the accounting. About 1 trillion yen spent, about 250 days of actual power generation across the reactor's entire history. The decommissioning order came in December 2016. 1 trillion yen is roughly $8.5 billion. Japan could have built a small city for that money. What it had to show for 3 decades of effort was a sodium fire, a cover-up scandal, and a reactor that had never meaningfully put power onto the national grid. France's experience was different in detail, but similar in outcome. Super Phoenix at Crays Malville was the largest fast breeder reactor ever built, 1,200 megawatts. It came online in 1986 as a flagship of French energy ambition. But over its 12 years of operation, it ran at the equivalent of less than 1 year at full power. Technical problems, sodium leaks, and public protests kept it shut for most of its life. When Lionel Jospin became Prime Minister in 1997, his government included the Green Party as a coalition partner. Closing Super Phoenix was part of the deal. The reactor shut down in December 1998. Its average lifetime capacity factor was roughly 7%. For every 100 units of electricity it was designed to produce, it managed about 7. The United States had a different story, and in some ways, the most painful one. The Integral Fast Reactor program at Argonne National Laboratory in Illinois was not a failure of engineering. By 1994, the project had solved the hard technical problems. It had demonstrated passive safety. If the cooling flow dropped, the reactor slowed itself down with no operator action needed. The engineers called it a walk-away safe system. The word they used for it wasn't dangerous. It was the opposite. 2 years before the program would have been complete, Congress defunded it. The vote came in 1994, driven by post-Cold War budget pressure and lobbying from anti-nuclear groups. The scientists at Argonne argued that their reactor was different, that the hard work was done, that the finish line was close. They lost the argument in a committee room, not in the reactor hall. So by the late 1990s, the field looked like this. Germany had abandoned its reactor before it ever ran. The United States had cancelled a program within reach of completion. France had shut down its reactor to satisfy a coalition partner. Japan had damaged its own program with a cover-up, then spent 2 decades trying to recover from it. Only Russia continued building. Its BN-800 reactor at Beloyarsk eventually reached full operation in 2016, and Russia stayed in the game. And India, still building, still behind schedule, still there. The question nobody in the Western press was asking was why. India's answer had been written decades before the PFBR existed. In 1954, physicist Homi Bhabha laid out a 3-stage nuclear plan built around an awkward fact. India had little uranium compared with its needs. Estimates put its uranium reserves at about 70,000 tons, yet the country held about 319,000 tons of thorium, close to 1/4 of the known global supply. Thorium sounds like the obvious fuel, but it can't start and sustain the needed chain reaction by itself. It must first be changed into uranium-233 inside a reactor. That left India with a locked fuel store and no direct way to open it. Bhabha's plan was the key. Stage 1 would use India's natural uranium in pressurized heavy water reactors. These plants would make electricity and produce plutonium in their used fuel. Stage 2 would place that plutonium inside fast breeder reactors. The breeders would make more plutonium from uranium-238. They could also change thorium into uranium-233. Stage 3 would then use uranium-233 with thorium, opening a domestic fuel supply that could last for hundreds of years. Each stage feeds the next. Remove the breeder reactor in the middle, and the chain breaks. India can build normal nuclear plants, but it can't reach its thorium at scale. The PFBR was therefore more than one new power station. It was the narrow bridge between the fuel India lacked and the fuel India had. That made failure costly. It also made cancellation worse. India began building experience at Kalpakkam long before construction of the PFBR. Planning for the fast breeder test reactor began in 1969. The smaller test reactor reached criticality in 1985 and gave Indian teams direct experience with fast neutrons, plutonium fuel, and liquid sodium. That experience mattered because sodium systems don't forgive casual mistakes. Pipes must stay sealed, heat must keep moving. Pumps, valves, welds, and sensors must work in a hot metal circuit that operators can't inspect like an ordinary water pipe. The primary sodium passes through the reactor core and becomes radioactive. It then gives its heat to a second sodium loop. That loop heats water in a steam generator. Keeping the radioactive sodium away from water adds another barrier, but it also adds more pipes, pumps, and places where something can fail. India spent nearly 40 years working with these systems before the PFBR reached criticality. Even then, the larger reactor was a far harder task. Bhavani was formed in 2003 to build and run it. Construction began in 2004, with completion planned for 2010. The first estimate was about 3,492 crore rupees. The 2010 deadline passed. Then came revised targets for 2012, 2015, 2017, 2019, and 2022. Supply problems slowed work. Parts had to be changed. Sodium systems required more tests. The first budget grew to more than 6,800 crore rupees by 2020. From the outside, it looked familiar. Another breeder reactor swallowing money while the finish line kept moving away. But India's leaders faced a choice that Germany, France, Japan, and the United States did not. They could cancel an expensive reactor, or they could cancel the middle stage of a 70-year energy plan. So the work continued. By 2023, something had changed at Kalpakkam. Workers finished filling the primary and secondary sodium circuits. That process alone took careful months. Sodium is liquid above about 98 degrees Celsius, roughly the temperature of very hot bath water. Filling an entire reactor system with it means keeping the metal warm throughout, monitoring every pipe, watching for leaks with instruments rather than eyes, because you can't see sodium the way you can see water dripping from a joint. When the circuits were full and stable, the team began the final sequence: loading fuel, checking instruments, bringing the reactor carefully toward a self-sustaining chain reaction. A reactor reaches criticality when the neutrons released by splitting atoms are exactly enough to keep splitting more atoms at a steady rate. Below that point, the reaction dies out. Above it, it grows. At criticality, it sustains itself. On July 4, 2024, the PFBR crossed that line. India's Department of Atomic Energy confirmed it. Prime Minister Modi marked it as a historic moment. Reuters and The Hindu reported it. For a day or two, it ran in international headlines, then it faded, crowded out by other news. But what had actually happened was precise and took a long time to understand from the outside. India had become the only country outside Russia to start a new fast breeder reactor in the 21st century. Not the only developing country. Not the only country in Asia. The only country, aside from Russia, anywhere on Earth. Every other nation with the technical capability to attempt it had walked away. India had been the one still building. Part of what made this possible was a decision made under pressure decades earlier. When international sanctions hit India's nuclear program after the 1974 Pokhran test, the restrictions went wider than most people realized. The Nuclear Suppliers Group cut off not just nuclear fuel and reactor parts, but industrial components that India needed for almost any advanced manufacturing. Valves, pumps, precision sensors, measuring instruments used in engineering more broadly. The intent was to limit India's nuclear reach. The effect was different. Engineers at Bhavini and companies across India's industrial base had to develop what they couldn't import. Larsen & Toubro worked on large fabricated components. Godrej Industries built specialized manufacturing capability. Bharat Forge, a company whose primary business was making parts for trucks and cars, developed nuclear-grade forgings that international experts had once said couldn't be made outside dedicated Western facilities. None of this was fast, none of it was cheap, but by the time the PFBR needed these parts, India had the capacity to make them domestically. That industrial depth doesn't appear on any single balance sheet. It lives in the knowledge inside engineering teams and the tooling inside factories, and it compounds. Each time a company solves a hard fabrication problem for a nuclear project, the capability stays. The next project starts from a higher floor. This is the part the graveyard comparison misses. Germany, France, the United States, and Japan all tried fast breeders in an era when they had access to global supply chains. They didn't need to build everything themselves. When the politics changed and the projects were cancelled, nothing was left except the hardware, which was decommissioned or turned into a theme park. India built under restriction. It built slowly and over budget, but the building itself created something that outlasted any single project deadline. That matters now because the PFBR is not the end of the plan. India's Department of Atomic Energy has announced plans for 6 more fast breeder reactors. 2 of them, rated at 600 megawatts each, are already in the planning stage at Kalpakkam. They would sit near the PFBR, using the same site infrastructure, the same sodium expertise, the same engineering teams. The logic is deliberate. Stage 2 of Baba's plan doesn't work with 1 reactor. It works when a fleet of breeders produces enough plutonium to fuel subsequent breeders, building a stockpile that grows over time. 1 reactor generating 500 megawatts is a proof of concept. 6 reactors generating 500 to 600 megawatts each, with more to follow, is an industrial program. The gap between those 2 things is large. Building the first was the hardest part technically. Licensing it, operating it safely, refining the fuel cycle, training the people to run it, all of that takes years. But the institutional knowledge that India built over 4 decades at Kalpakkam is now embedded in Bhavini, in the companies that fabricated its components, and in the engineers who watched the sodium circuits fill and the neutron count rise toward criticality. That knowledge doesn't transfer easily. Russia has it because Russia never stopped. India now has it because India kept building when everyone else stopped. Here is where the geopolitical layer becomes clear. India imports about 85% of its oil. It depends heavily on coal for electricity. Its uranium is limited. In energy terms, it is exposed. The countries that supply fuel, or that control the technology to process it, hold significant leverage. That is what energy dependency actually feels like in practice. A country can't easily refuse demands from a supplier it needs. It can't easily absorb sanctions imposed by a technology-controlling group. Every time the price moves in an international energy market, the pressure transmits directly into India's economy. The 3-stage nuclear plan doesn't just offer cleaner electricity. It is a plan to reach a position where that leverage no longer applies. A country running on domestically bred thorium fuel, using reactors it designed and built itself, is not easily coerced through energy supply. This is the part of the story that gets the least coverage. The PFBR produces headlines as an engineering feat. It is harder to photograph the geopolitical consequence. The steady erosion of a lever that powerful states have used against India for 50 years. The sanctions period after 1974 showed exactly how that lever works. Western governments restricted not just nuclear materials, but the ordinary components needed to build complex industrial equipment. The intent was to make the three-stage program too difficult to complete, but the restriction that was meant to prevent indigenous capability ended up creating it. Bharat Forge makes nuclear-grade forgings now. Larsen and Toubro can fabricate complex reactor components. Those capabilities exist because India had no other choice but to build them. A foreign policy decision made in the 1970s to suppress India's nuclear program contributed, in a roundabout way, to making India's nuclear program self-sufficient. There is an irony in that worth sitting with. The PFBR is currently in what engineers call the power ascension phase. After reaching criticality, a reactor doesn't switch to full output immediately. Operators raise power in careful steps, testing each system at each level, building confidence in the full operating envelope before moving higher. The PFBR is working toward its rated 500 megawatts. Full commercial operation is expected within the next year or two. When that happens, Stage 2 of the plan will be genuinely underway.